Okay, we'll get started. We're going to be starting with 3C, so that's a new unit, and we're going to be talking about the concepts of weight and mass. So you've probably heard those two terms, but they have very specific physics meanings. These two concepts are related, but we're going to look at actually some of the differences. So again, any object is really going to have both weight and mass. We'll have both of those. So we'll start with the definition. So mass, that's the amount of material in an object. That's from, we just talked about that the previous notes. So again, not how big it is, but how much stuff is in it. Weight is a little bit different. So weight is actually the force of gravity. It's a type of force that's pulling down on an object. So the force of gravity is going to be, it's a new type of force. It has F with the little subscript uppercase G, and that's going to be from a planet. So the force of gravity is that's the force that's pulling down on the surface of a planet. So if you have a planet right here, you can have an object, and the force of gravity is actually going to be pulling down on it. So next thing is what's a scalar? What's a vector? Mass would be a scalar. Weight would be a vector. Because mass does not have a direction. You don't say 5 kilograms in a direction. It's just 5 kilograms. Weight does have a direction. As you saw right here, there's an arrow pointing down. In this case, because it's being pulled down by the planet, it's important that it has a direction because it is a force. The units, mass is the kilogram. So again, we've seen that before. Weight is the Newton. So it's important to note that these things are measured in completely different units, and they're not necessarily equivalent to each other. For example, if you have 5 kilograms, that's not the same thing as saying 5 newtons. They're, the units, the newtons, kilograms, are representing completely different things. This would be a mass. This would be a weight. So keep that in mind. Make sure you have the same units. The units are not the same thing. And the last thing in this table is what's the difference on other planets. Mass does not change on other planets. So if you bring an object, on Earth, on the Moon, Pluto, it's all the same. There's no change. Weight changes. So weight actually depends on the acceleration of gravity on that planet, or little g on that planet. So if you have, the Earth, oddly shaped Earth, and you have the Moon. Draw that over here. So if you have Earth and then you have a smaller planet, the Moon, their acceleration due to gravity are actually going to be different. So you're going to be accelerated differently on Earth, the Earth, than the Moon. And that's important. So your weight's actually going to change on different planets. Mass will not. Mass is always the same on any planet. You bring it anywhere in the universe, will still be the same. So weight and mass, you can actually relate them. There's an equation that shows that they are related. It's this equation down here. So weight, which is equal to Fg, remember F subscript G. So F subscript G, that's the force of gravity, G for gravity. That's equal to m times little g. So m times little g, that's the mass right here, mass. And this little g is the acceleration due to gravity. It's actually the magnitude of acceleration due to gravity. So it's the size of acceleration on that planet. The little g itself does not include a direction. So little g is going to be positive. So again, it's positive because it's just the magnitude. Magnitude would not be positive and negative. It's just the size, how big or small something is. And little g on Earth is going to be 9.2 meters per second squared. Remember, little g on Earth is not going to be negative. It's just going to be a positive number because little g is the magnitude, it's the size, it's how big the acceleration due to gravity is. So that's really it for the notes. So again, what do we talk about? Mass, weight, the differences between the two. and there are quite a few. And then there's an equation that actually can relate mass and weight together. And again, talking about what that little g means, it's the acceleration or the magnitude of the acceleration due to gravity. So a little bit less material than the last unit, but we're going to do a quick example problem. Here we go. Okay, so please, before I start this problem, make sure you have it written down eventually, but take, maybe a couple minutes to see if you can solve it, see how you do, and then I'll pick up with the solution. So I'd take maybe a couple minutes to see if you can solve it. So solving it, making sure you're not on Facebook or Instagram or solving. Okay, I'll do the solution out right now. Hopefully you had a little bit of time to at least get a start on the solution. So it says a rock has a mass of 5 kilograms on Earth. Okay, Earth 5 kilograms. So what is its mass and weight on Pluto? So a different planet. So the magnitude and sorry, quick typo. This should not be Pluto. Doesn't really make a difference. Sorry, this should be Neptune. Neptune. So it's asking so if you have a mass of 5 kilograms on Earth, what is the weight and the mass on Neptune, not Pluto? So it asks us for that, and then it gives us the information. The magnitude of that acceleration is going to be 11.2 meters per second squared. So the acceleration due to gravity on Neptune is 11.2 meters per second squared. So we got the mass on Earth is 5 kilograms. Here we go. Now we're looking for the mass and the weight on Pluto. So we're looking for mass, and I'm going to write weight as force of gravity on Pluto. Neptune equal to question mark. So we do not know that. So we got to figure that out. The mass is the easy part. So the mass is going to be equal to 5 kilograms. Because mass does not change. Doesn't matter if you bring it to Neptune or Pluto or deep space, the mass is always constant because the amount of stuff will not change. There we go. Now we're going to calculate the weight on Neptune. So the weight. So to do that, we're going to use the formula. So weight is really the force of gravity. It's m times the acceleration due to gravity on that planet. So it's going to be mass. So we know the mass is 5 kilograms. The acceleration due to gravity is given to us. On Neptune, it's a little bit different. So it's 11. It's not 9.8 because it's on a different planet as Neptune. So it's 11.2 meters per second squared. So if we do that out, we just do the multiplication, we're going to get 56 newtons would be the weight. So that is all the pieces to the problem. So it asks us what is the mass, what is the weight on another planet. The mass is going to stay the same, 5 kilograms. The weight's actually going to change because little g is going to vary on different planets. On Earth it would be 9.8, but we're not on Earth, we're on a different planet, we're on Neptune. It's actually going to be 11.2 meters per second squared. Okay, so that was the notes. Again, the goal, mass versus weight. So we talked about that, and then we also talked about, we also did kind of a sample problem. Okay, that's it for now. Make sure you have this copied down. Make sure your notes are annotated.